Welcome to the sixth video of our class. The last class, we have a brief introduction of what are the enzymes and how are they classified. We'll have a small recap. The enzymes are basically classified into two types. They are extracellular and intracellular. Extracellular are those which are present outside the cell, for example, the digestive enzymes. On the other hand, intracellular are those which are synthesized within the cell. As per the IUB, International Union of Biochemistry, all the enzymes are classified into six different groups, and they are oxidoreductases, then transaminases, followed by hydrolases, then lyases, isomerases, and ligases. As you know, for an enzyme to show its activity, it should first bind to a substrate and form enzyme substrate complex, and then it forms the products. You might be aware of lock and key hypothesis or induced fit hypothesis. Consider the enzyme to be a lock and key to be a substrate. To open a lock, the substrate has to be a specific and bind to the lock, and then it opens. Similarly, for every enzyme to show its activity, there should be a specific substrate to it. Then only it shows the activity. Basically, enzyme binds to the substrate to form enzyme substrate complex and gives out the product. As a result, the enzyme remain intact even after the reaction, which means enzymes are playing the role of catalyst. And you know, catalysts are those which participate in the reaction, increase the rate of reaction, but does not undergo any change in its physical structure or nature. Basically, for an enzyme to show its activity, there are certain factors that favor. Those factors affect the enzyme and substrate activity. So in this video, we'll be seeing what are those factors, how are they affecting it, and also try to see the kinetics of it. Moving on to the factors affecting the enzyme activity are, let us begin with the factors affecting enzyme activity. Beginning with the first one, and that is concentration of the enzyme. As you can see, as concentration of the enzyme increases, velocity of the reaction also increases in a proportionate way. So greater the number of substrate, greater will be enzyme substrate complex. So as the concentration of the enzyme increases, you can see the enzyme concentration and rate of velocity, right? So as the concentration is increasing, enzyme velocity will also increase. Depends on the concentration of the substrate as well. Next one is concentration of the substrate. Increase in substrate concentration, okay, increase in substrate concentration increases the velocity of the enzyme reaction. Increase in substrate concentration increases the velocity of the enzyme reaction in a limited range. That is, if suppose you can see the graph here, this is a substrate concentration on the x-axis and velocity or rate of reaction on the y-axis. As the concentration is increasing, velocity is also increasing up to a certain point, and then it is steady. It will be a straight line like this. It won't increase further. It will be a straight. That means there are no more substrates to bind with the enzyme and form the reaction, undergo the reaction. So since substrate concentration is limited, even this curve is showing the steady state. You can see a rectangular hyperbola. Hyperbola means the plot that we get is a rectangular hyperbola. How is it rectangular hyperbola? When we get this curve and we extrapolate this line, okay, we get a rectangular plot, right? Rectangle, not exactly the rectangle, but four-sided figure. That is perpendicular to the line that we have got. To this, the perpendicular line is this one, and it here the perpendicular line is this one. So this is called rectangular hyperbola. Okay, it has three different distinct phases: A, B, and C. A is the initial, which is increasing as the concentration of substrate is increasing. B is a slight curve, and C the steady state. Now we'll see the kinetics of enzyme activity. There is a constant called Michaelis-Menten constant. How do we get that constant? What is the equation behind that? And we'll also see Lineweaver-Brook plot, which is a reciprocal of Michaelis-Menten constant. As you know, enzyme plus substrate, right, gives enzyme substrate complex. This is a reversible reaction,
and this gives enzyme plus products. Enzyme is intact. So this is the first step, this is the second step, and this is the third step. So the rate of reaction for this is K1, K2 and K3. There is a constant called as Michaelis-Menten constant denoted by Km. Michaelis-Menten constant. This Michaelis-Menten constant is written by the formula Km is equal to K2 plus K3, that is a second and third reaction addition, and divided by K1. On further simplification with the velocity of the reaction, it is written as V is equal to Vmax into S, that is substrate concentration, divided by Km plus substrate concentration. Okay, what is Vmax? We'll see now. Consider this plot. On the x-axis concentration of the substrate, and this is the rate of reaction. As concentration of substrate increases, rate of reaction also increases up to some point and then forms like this, a steady. Isn't it? This is a steady state, and this is Vmax. So this whole is the Vmax, and that Vmax is here. Okay. The Michaelis-Menten, based on the Michaelis-Menten's equation, they have assumed this Vmax to be half. Suppose this is 1, then half of this position from here to here, it will be 1 by 2. So 1 by 2 Vmax. What they have done is, in place of V, they have taken 1 by 2 Vmax is equal to Vmax into S divided by Km plus S. We'll see how further it is simplified. I'll draw the graph here once again. S and R, this is the Vmax, and this is half Vmax. So I'll just put a line like this and this one like this, and this is Km. Okay, and the equation that we got above was 1 by 2 Vmax is equal to Vmax into S by Km plus S. I'll take this whole part this side, then it will be, and this Vmax to this side. So Km plus S into Vmax is equal to, this 2 comes here, 2 into Vmax into S, right? Now I'll take Vmax here, so Km plus S is equal to 2 into Vmax into S by Vmax. This Vmax and Vmax can be cancelled, right? Now what will be the remaining? Km plus S is equal to 2 into S, 2S. So Km is equal to 2S minus S, which means Km is equal to S. This means Michaelis-Menten's constant is proportional to concentration, which also mean increased Km or high Km value means low binding. Why is it low binding? Km is proportional to substrate, right? If substrate concentration, that is free substrate, is more, that means the enzyme is not binding with the substrate properly, which also means the binding is less. Similarly, low Km means greater binding. I hope you are clear with this. This was Michaelis-Menten's constant. Once again, we'll have a recap. Enzyme kinetics, enzyme plus substrate gives enzyme substrate complex and gives the product. This is a K1, K2 and K3. You can see the graph. S is a substrate free substrate, and this is the rate of reaction. It increases at up to a certain point and be a steady when substrates are completed. And this one is the half of V max. Okay, and Km value is equal to, the equation is K2 plus K3 by K1, and upon applying algebraic calculations we get V, that is measured velocity, is maximum velocity into substrate concentration by Menten's constant plus substrate. And in place of this V, we can, when we assume it to be half, that is half V max is equal to, this will be the equation. Upon further simplification we get all these, the 2 goes here, this part comes here, and Vmax comes here, Vmax gets cancelled, and finally we get Km is equal to this one. So as per the graph we can write Km is so as per this we can define Km as concentration of substrate required to produce half of the maximum velocity of enzyme catalyst reaction. Once again, Michaelis-Menten constant can be defined as substrate concentration required to produce half of the maximum velocity. This is Michaelis-Menten's constant. Beyond this is another line viewer Brook plot. This plot is reciprocal of Michaelis-Menten's constant. What was the equation that we got? V is equal to Vmax into substrate by Km plus S. This was the equation that we had in the beginning. If we apply the reciprocal form to it, what will happen? 1 by V is equal to 1 by Vmax into S by 1 by Km plus 1 by S. This can be written as 1 by V is equal to, this comes up and this comes down, Km plus S by Vmax into S. This, upon further simplification, 1 by V is equal to Km by Vmax, right, into 1 by S plus S by Vmax into S. This S and S gets cancelled, so we get 1 by V is equal to Km by Vmax into 1 by S plus 1 by Vmax. And looking at it we get an idea. Suppose this is Y is equal to, let this be A, so A let it this be x and this one b, ax plus b. This is the equation of a line. So let this be a, let this be x, and this let this be b. So this is y. Y is equal to ax plus b, and this is the equation of a line. As per this, we need to get a graph. So this is 1 by v max. Okay, normally v will be here, but 1 by v max reciprocal of it is here. Suppose this is 10 and here it will be 1 by 10. Similarly here v max, here it is 1 by v max. Okay, if we extend this one, this is the negative side, this is the positive side, right? This is the negative side, this is the positive side. So this one will be, here we had km, here we had km in the beginning, so here it will be minus 1 by km, and this is the slope, and slope is km by Vmax. This is Line-Weaver-Brook plot.
Moving on to the third factor, that is effect of temperature. As you know, all the enzymes are heat labile. They get denatured by increased temperature. So you can see the graph, as temperature is increasing, okay, the velocity is also increasing up to a certain point, that is until 40 degrees. Beyond 40 degrees, you can see there is a decline in the graph, which means at this temperature all the enzymes are getting denatured. As a result, there is no enzyme present to bind with the substrate and form enzyme substrate complex and give out the product. So the graph that we got is a bell-shaped graph, or we can call it as bell-shaped curve. So the optimum temperature is, you can write either 40 or 45, or you can write the range 40 to 45 degrees centigrade. And sir, some enzymes are active even at 100 degrees centigrade, but they are exception. In general, all the enzymes temperature exposed to a temperature above 50 degrees or beyond 45 degrees get denatured, leading to dearrangement in the native tertiary, that is denaturing of the protein. And one more thing is, you need to remember a Q10. Q10 means temperature coefficient. What it means is, for every 10 degrees rise in temperature, rate of reaction increases. Which means for every 10 degrees increase in the temperature, the speed of the reaction of an enzyme increases. And the optimum value is 2. The Q10 value, if it is 2, it is the optimum value, which is between 0 to 45 degrees centigrade. Let us begin with the next factor, that is effect of pH. pH is the concentration of H plus ions. Okay, and as you can see the graph here, this is the pH value which ranges from 0 to 14, and 0 to 6.5 is acidic, 7.5 to 14 is the alkaline, 6.5 to 7.5 can be called as neutral, but basically 7.0 is the most neutral point. Okay, and you can see the graph, as concentration is as the pH level is increasing, the enzyme velocity is also increasing up to a certain point, that is the neutral point at 7. Further increasing the pH result is leading to a decrease in enzyme velocity. This could be, in acidic condition the enzyme is getting activated, whereas in basic condition, that is in alkaline condition, the enzyme is getting deactivated. So you can see an increase in hydrogen ion concentration influences the enzyme activity, and we get a bell-shaped curve. Okay, and in each enzyme has optimal pH at a velocity at which the velocity is maximum. At optimum pH, that is at 7, velocity is maximum. Most of the higher organisms show optimum activity, that is between 6 to 8. I've said 6.5 to 7.5. Let us consider it to be 6 to 8. However, There are certain exceptions like pepsin, which is a digestive enzyme which is active in 1.1 to 2 pH, and acid phosphatase, which is active at 4 to 5 pH, and alkaline phosphatase active at 10 to 11 pH. All these are the digestive enzyme which helps in digestion. Next is the effect of product concentration. What is a product concentration? When enzyme and substrate combine, they form enzyme substrate complex followed by the product formation. If the product formation is more, that means substrate concentration is decreasing, isn't it? Enzyme concentration is more, substrate concentration is decreasing, which also means there is no more substrate left to bind with the enzyme, right? Which also means the enzyme is not getting complex with the substrate. As a result, there is no reaction with the protein or the enzyme. So you can see accumulation of enzyme or accumulation of reaction products decreases the enzyme velocity. And for certain enzymes, the products combine with the active site of enzyme and forms a loose complex and thus inhibit the enzyme activity. What it means is the product that we obtain, this product attaches to the active site of the enzyme instead of substrate and inhibit the enzyme. When the product is getting attached to the protein, substrate cannot come and attach there to show the activity. That means the product is inhibiting the amino acid. So in living systems, this type of inhibition is generally referred by a quick removal of products from. Okay, this point is not required. And the next is uh, effect of activators.
In the previous classes, we have seen, especially while dealing with glycolysis, we have seen various enzymes, that is glucose getting converted to fructose. For it to get converted, it needs isomerase enzyme. Then fructose was getting converted to fructose 6 phosphate. That means ATP was getting consumed. During that process, magnesium ion was required. That means a metal ion was required. Similarly, there are different um, reactions in different pathways where we have come across the requirement of manganese, copper, and especially in electron transport chain, where we have seen the proteins having iron, sulfur proteins, and the copper. All these were the metals present within the enzymes to show the activity. So in the effective activators, we'll be seeing how these are playing the role.
As you have seen, conversion of glucose to fructose in presence of hexokinase in glycolysis, we have seen Mg plus 2 magnesium ion. Similarly, many metal ions are used to catalyze a reaction. We have also seen copper ion, and in electron transport chain we have also seen iron, sulfur proteins, right? All these metal ions or metallic cations are required to activate the enzyme, which further undergoes reaction with the substrate and gives out the product. Okay, these are the 6 factors responsible for the enzyme activity.
These were the factors that were affecting the enzyme kinetics or enzyme activity.